Neural networks are at the heart of deep learning, and they're made up of layers of nodes, also known as neurons. But have you ever wondered how these neurons decide whether to pass information forward? That's where activation functions come in. Activation functions introduce non-linearity into the network, enabling it to learn complex patterns. Without these functions, a neural network would simply be a linear regression model, unable to handle the intricate relationships in data. Each activation function has its own characteristics and impacts the performance of the network differently. In a neural network, each neuron receives multiple inputs from the previous layer. These inputs are typically the outputs of other neurons and are multiplied by weights, which represent the strength of the connections between neurons. The neuron then sums these weighted inputs to calculate a single value, often referred to as the weighted sum or net input. This net input is then passed through an activation function, which determines whether the neuron should be activated and pass its information forward to the next layer. The process of multiplying inputs by weights, summing them, and applying an activation function is what allows neural networks to learn from data and make predictions. An activation function is like a gatekeeper for each neuron. When a neuron receives input data, it calculates a weighted sum. But instead of passing this raw sum straight to the next layer, the activation function steps in. It applies a specific transformation to this sum, determining the neuron's output. Linear activation function outputs the input as is. No non-linearity, so it's only useful in specific scenarios where a simple linear relationship is sufficient. Sigmoid activation squashes input to a range between 0 and 1, useful for binary classification, but can cause vanishing gradients in deep networks. Tanh activation, similar to sigmoid, but ranges from -1 to 1, centering the output and often used in hidden layers to mitigate vanishing gradients. ReLU, rectified linear unit, outputs the input directly if positive, otherwise outputs 0. Popular in deep networks due to efficiency and mitigating vanishing gradients. Leaky, a variant of ReLU that allows a small, non-zero gradient for negative inputs, preventing the neuron from dying during training. Softmax function. The softmax function is used at the end of a neural network to turn the output scores into probabilities. This helps in deciding which class an input belongs to, especially when there are multiple classes. The output values are between 0 and 1, and all probabilities add up to 1. The activation function as a gatekeeper ensures that only significant signals, those that meet certain criteria, are propagated forward through the network. By doing so, it adds non-linearity to the model, enabling the neural network to learn complex patterns and relationships, ultimately making it capable of performing tasks like classification, prediction, and recognition.